this will be probably my last lecture on free electron laser. In this lecture we will discuss the energy gain by the laser radiation from electron beam in a conventional rather untapered free electron laser, and then the energy enhancement by tapering the Wiggler, and also we like to view free electron laser from the perspective of stimulated Compton scattering. We shall essentially discuss the energy gain in untapered FEL that we were discussing last time, but we could not complete that discussion. So, we will continue with the discussion, and we will go over to see what a tapered Wiggler is and obtain potential energy buckets due to the ponderomotive force created on the or rather exerted on the electrons by the laser field and the Wiggler magnetic field, whose wave number is a function of position, and then what kind of phase space trajectories the electrons would have in that kind of ponderomotive force, and what is the estimate of energy gain by radiation, and then we will talk about Compton regime operation. Well, let me very briefly review that we are talking about the propagation of an electron beam in the interaction region of a free electron laser, which has a Wiggler magnetic field and which also has a radiation field. And the electron energy which is resonant, the electron velocity which is resonant with the beam particles is defined as V with the ponderomotive wave is called Vp, which is equal to omega upon k plus kw. Please remember that we are talking about the Wiggler magnetic field of this form Vw, which has some amplitude Aw polarized in the right handed sense and has a phase variation as exponential ikWz, and the laser field is left circularly polarized, which is equal to Al x minus Iy exponential minus I omega t minus kz. So, in presence of these two fields, obviously the laser also has a magnetic field which is Bl, which is equal to I k upon omega into El. So, in presence of these fields, the electron which is injected from outside with a velocity V0 in the z direction, this acquires velocities Vw and Vl, and the Lorentz force due to cross field terms essentially Fp on the electron is caused by minus E V due to the Wiggler cross magnetic field of the laser. This force is parallel to z axis, which is the direction of propagation. This is my z direction. So, the electrons experience a force, and in presence of this force we define a quantity called gamma r. If the electron is moving with a velocity equal to the phase velocity of this force, which is the phase velocity of this force, then I call this energy equal to gamma r, which I defined as 1 upon under root of 1 minus omega square by kp square c square, where kp I defined as the sum of the laser wave number wave vector plus the Wiggler wave number. So, gamma r certainly is a quantity quite large if omega upon kp is very close to c. Then we defined a quantity gamma, or rather we expressed particle energy gamma as gamma r plus some small departure from this value. And we wrote down two equations, one governing gamma, which was d gamma by dz is equal to Fp z over mc square. This is the energy equation. And one was the equation governing the evolution of phase of the wave. Phase of the wave we defined as kpz minus omega t, and we wrote down an equation for d psi by dz, and which was like kp minus omega by vz. Then we wrote down vz in terms of capital gamma. So finally we got two coupled equations, one for particle energy gamma and then phase of the wave as seen by the electron beam. And these equations in dimensionless forms were of this form. Let me just write these. D psi by d psi is equal to P, and the other equation was dP by d psi is equal to minus A cos psi. These two equations we combined together and we deduced a quantity, an expression for P in terms of psi, and that equation was of this form. P was equal to P0 square minus twice AP, or rather A, not AP, it's A, upon P0 cube into no, I am sorry, this is not right, this is not right. Let me delete this. The equation that we deduced was P square is equal to P0 square plus twice A sin psi in minus sin psi to the power half, where P0 is the initial energy with which the electron, initial value of P with which the electron is launched into the machine. A is the normalized amplitude of the quantum motive force. Psi in is the initial phase of the wave as seen by the electron when it is injected into the interaction region, and psi is the phase of the wave at any instant of time as seen by the particle. And I mentioned that we can solve this differential equation for psi and this equation for P, which is a measure of particle energy, iteratively. So what I do that I take the square root of this, it is not a square root here, sorry, there is no square root here, this is just this quantity. So we take the square root of the right hand side and express P in terms of or powers of A, and that we did last time. So what we obtained was this, let me write on the separate sheet. P is equal to P0 minus A upon P0 within bracket sin psi minus sin psi in minus half A square upon P0 cube sin psi minus sin psi I n square. What you have to do? The equation that we have to solve along with this one is d psi by d psi is equal to p. First we ignore a terms here. So, to the 0th order in powers of a. A is the amplitude of the pontomotive force. So, if pontomotive force is not there, if A is 0, then P equal to P 0, and if I use this P equal to P 0, then you can differentiate this equation, integrate this equation to obtain psi is equal to psi initial plus P times psi. This is what you will get. Here I have presumed that at xi equal to 0 or z equal to 0, the phase of the wave as seen by the particle psi I n. And then we go over to the next order. Let me call this result as psi 0. So, this is the 0th order P and 0th order psi when effect of wave, pontomotive wave is not there on particle trajectory. To the next order, we use the value of psi equal to psi 0 in the expression for P, use psi equal to psi 0 in P expression for P, and we get P is equal to P 0 minus A upon P 0 sin psi 0 minus sin psi I n. And if you use this value of P in the psi equation, you will get psi 1, psi becomes then psi 0 plus psi 1, where psi 1 turns out to be equal to AP, rather A upon P, sorry, not AP, A upon P 0 multiplied by 1 upon P 0 into cos psi 0 minus cos psi I n plus xi sin psi I n. Then we go to the second order, and when you go to the second order, in A square, when you retain these terms, P can be written as P 0 plus P 1 plus P 2. P 1 and P 0 P 1 I had already given. So, P 2 turns out to be, from this expression for P square, you get P is equal to, P 2 is equal to minus A square upon twice P 0 cube into sin psi 0 minus sin psi I n square minus A upon P 0 cos psi 0 into psi 1. This sort of expression you get for P2. This is the important thing where psi 0 is related to the initial phase psi in plus initial normalized energy into distance of propagation, normalized distance of propagation. So, we have really got the particle sort of energy as a function of xi. Xi is coming in a little complicated fashion through psi 0. There is no explicit dependence on psi. It is coming slightly in a complicated fashion through psi. So, xi dependence or z dependence of P2 is through psi 0 or xi. Now, the issue is I want to find out what is the energy gain of the electron or energy loss of the electron, net energy loss by the electron. So, net or rather I would like to find out normalized energy gain by radiation. If I treat P as some sort of a normalized energy with respect to gamma r, then the normalized energy gain by radiation is the same thing as the decree initial energy of the electron minus P at a value xi is equal to 1, because xi equal to 1 means z equal to L. So, this is the particle energy in the beginning, this is the particle energy at the end. So, this is the energy going to radiation. And I would like to obtain this quantity as an average over all the particles, electrons that are entering the interaction chamber between phases 0 to 2 pi. So, psi in is varying from 0 to 2 pi. So, what should I do? I get this quantity integrated over d psi in and integrate from 0 to 2 pi and divide by 2 pi. This is the normalized average energy gain by radiation per particle when it is averaged over all the phases of the particles. So, this should be within the bracket. This is P0 minus P evaluated at xi equal to 1. I can rewrite this expression. Please note here, if I put the value of P here, P0 minus P0 will cancel out. P1, if you evaluate the expression for P1 d psi in, is time average is 0 if you just look at the expression for P1. And if you, this is only P2 that survives here, and that gives rise to finite energy gain by the radiation. That is why I had to go to evaluate P2. So, it is this term which is important in energy transfer from particles to wave, and this turns out to be simply equal to, put this here, this is P2 with the negative sign of course, and I am evaluating this xi is equal to 1 multiplied by d psi in upon 2 pi and 0 to 2 pi. There is a negative sign already in minus outside here and these terms, and you can take care of this one positive. And let us evaluate this quantity and let us see what do we get. This can be done easily, and the result turns out to be the energy gain by radiation, energy gain normalized by radiation. This quantity is, let me call energy gain maybe delta E per particle. It turns out to be AP square upon P0 cube and 2 sine square P0 by 2 minus P0 sine P0 by 2 into cos P0 by 2. And the interesting thing is that this quantity can be expressed in a compact form if I define P0 by 2 as x. Suppose I define a quantity x like P0 by 2, then the energy gain turns out to be equal to, actually this is normalized energy gain, so let me put a prime somewhere because it is a normalized quantity, so put a prime there. And this turns out to be equal to A square, well by mistake I have put AP, this is simply A, the amplitude, square by 8 into g of function x, where g of x is minus d dx of sine square x upon x square. This is a very interesting function, and if you plot this as a function of x, please remember x is the difference of initial. I think it will be useful if I write this x explicitly in terms of energy. This turns out to be equal to L Kp into gamma of the electrons in the beginning minus the resonant gamma divided by 2 gamma r square minus 1 into gamma r. So, this is the departure of electron initial energy from the resonant energy. This was the essentially the energy available, sort of energy available with the particle if you multiply by mc square. So, this is the important parameter on which this gain factor g depends. How much is the value of g? If I plot this, it turns out to be like this. Plot g here and x there. The values may be like 2 may be here, 4 may be there, minus 2 here, minus 4 there. This function is 0 when this is 0 and the peak value is around 0.6. So, it is 0.6 and this is minus 0.6 here. So, this function has a peak of 0.6 around 1.5. So, this is and this becomes 0 around 3, this goes like this. This sort of behavior it gets. So, this function gain is positive only when x is positive and it peaks at a value of x around 1.5. It peaks at x equal to 1.5 and the maximum value of g at that point is around 0.6. The net energy gain by radiation, single particle energy gain, will be proportional to the square of laser amplitude, square of the Wigler amplitude, and it will be, this factor will be around 0.6 if you have chosen your initial energy of the electron beam in such a fashion that this quantity is around 1.5. That is a very important deduction from this analysis that one should always have a beam moving faster than the quantum motive wave. So, that gamma 0 is bigger than gamma r, and these are the normalized parameters. You should choose that value. Now, in an oscillator what really happens, or even an amplifier what happens, as the radiation grows at the expense of beam energy, because radiation is getting energy from millions of particles. So, its amplitude really grows up, then A evolves, this amplitude A evolves with distance, and in this formalism we have not considered that. So, people carry out this calculation numerically, and then they can get the energy gain. And by this technique you can have energy gain typically of a few percent in a free electron laser, maybe a percent or few percent of that order. In order to increase the efficiency of the free electron laser, you need to devise ways to retard the electrons more efficiently than by simply the quantum motive wave. Now, what can happen? We can get a clue for this in one way, that the quantum motive force traps the electrons, and if you can slow down the quantum motive wave. Now, quantum motive wave can slow down means what? Quantum motive wave moves with a phase velocity Vp, which is omega upon k plus kw. If you can have a wiggler whose wave number can be modulated, can be reduced with z, wave number can increase with z. Suppose I make this a function of z, increasing function of z, then Vp will go down. So, what will happen? This is the quantum motive wave which traps particles somewhere here, and if you can slow down the quantum motive wave by making this ripples closer, so the wave number increases, then the electrons which are trapped by this wave, they will be forced, if you can trap the electrons in potential energy minima, and those electrons are then retarded by force. So, by retarding the quantum motive wave, by making kw as a function of z, increasing function of z, you can get much higher energies, and this scheme of retarding the quantum motive wave is known as tapering, and this kind of FEL is called tapered free electron laser. So, we would like to find out what is the effect of making kw as a function of z. I do not think I am going to go into details of this, but the physics I can reveal in a simple way. Consider a tapered FEL, tapered wiggler. I am choosing kw as a function of z. I can write down the wiggler field as Bw is equal to some amplitude Aw x cap plus I y cap, and this I will write down as plus I integral kw dz, because this is a function of z. So, this is some sort of a WKB representation for the wiggler field. Some people make wiggler tapered by making Aw also as a function of z, but I will consider, for the sake of simplicity in physics, let me consider this. Then what is happening? The resonant energy that we define, gamma r, this be a function of z, because gamma r we defined as under root of 1 minus Vp square by c square. So, whenever the phase velocity of the quantum motive wave is a function of z, increasing, rather Vp is a decreasing function of z, gamma becomes a increasing function of z, and you can choose this. So, in a tapered wiggler FEL, d gamma r by d z is bigger than 0. You choose a finite value. So, what is happening? You want that the quantum motive potential energy well should be able to localize or confine the particles, and then the entire potential energy minima is slowed down. This is like trapping water in a bucket. In a bucket, if you have something and slow down the bucket, then the energy from the particle will go to the force that is retarding, and that is the beauty here. So, you want to retard the particles, and the equation of motion would be something like this: d gamma by dt, this is the energy equation, with mc square is equal to minus EEL dot VW. This is the energy equation that we have been writing for free electron lasers. We define a quantity gamma as gamma minus gamma r, but treat this gamma r as a function of z. So, what I am writing is gamma, I write in this equation as gamma r plus capital gamma. Then this equation for capital gamma takes the following form: d gamma by dz turns out to be equal to quantum motive force upon mc square, this is the z direction, minus d gamma r by dz. This I have to write explicitly here. This is the additional term that you get here. Subsequently, when you normalize your quantities and write this equation in terms of a quantity p by d psi, this equation is minus a cos psi, plus there is a additional term because of this, because d gamma r by dz is positive. So, this comes out to something like minus alpha 0. If the wiggler is not tapered, then this is 0, but because if this is tapered, then this turns out to be like this. And the equation governing psi is d psi by d psi is equal to p. So, basically there is a change that occurs in this set of equations through this quantity alpha 0. You can combine these two equations to obtain dp by d psi and integrate that equation, and what you get is this. So, when you integrate that equation, you obtain I made a mistake here. This gamma r, really I want a decreasing function of z, because I want gamma r, the particle quantum motive force phase velocity, to be decreasing. So, I want d gamma by dr to be negative, hence this becomes positive. I made a mistake in there. So, when you solve this set, you get as the integral p square by 2 plus a sin psi minus alpha psi is equal to a constant of integration, which I call h, and this can be evaluated by using the initial conditions at some point when at the entry point psi is psi in, p is p in or p0, then you get h is equal to p initial square upon 2 plus a sin psi initial minus alpha psi initial. This equation again represents trapped particles, but the character is quite different now. First of all, you can consider this to be some sort of a kinetic energy of a particle, and this some sort of a potential energy of a particle, this some sort of a Hamiltonian. So, this quantity is denoted by V, a function of psi, which is equal to A sin psi minus alpha, this is alpha 0 actually, I made a mistake, this alpha 0 into psi. If I plot this quantity as a function of psi, plot V psi as a function of psi, this turns out to be having this sort of shape. These are maxima and minima, maxima, minima in the potential energy as a function of psi. The particles can be trapped between these potential energy minima, around this potential energy minima. And when this potential energy minima is slowed down, as the entire potential, this bucket is slowed down, the energy goes from particles lose energy. And after all, this potential energy is essentially is a function of laser amplitude. So, the energy really goes into the laser. So, you are forcing the electrons to slow down, and the condition for trapping turns out to be the particles should be trapped. There should be a minimum here in potential energy curves, only the particles will be trapped, and the condition turns out to be, if we want d psi by dV by d psi equal to 0 for minima to occur, then you require that A should be bigger than or comparable to alpha 0. This is a necessary condition. So, if you can choose a bucket or laser field of finite amplitude, then this condition can be satisfied, and the electrons that are trapped in these buckets, those electrons will be retarded forcibly by the retardation of the quantum motive wave, and then the energy that they gain is of this order. Let me give you a final result about energy gain. The energy gain turns out to be typically of this order. Energy gain efficiency actually. This is defined as the energy gain by radiation divided by the initial kinetic energy of the electron beam, and this turns out to be delta psi by 2 pi and gamma r at the entry point minus gamma r at the exit point where xi is equal to unity divided by gamma r at 0 minus 1. This is the, if we multiply by mc square, this is the initial kinetic energy of the electron beam. This is the, if the electron beam I consider to be moving very close to the velocity Vp, and this is the energy it has lost. So, this is the efficiency. Delta psi is the spread, the width of the bucket. As I showed to you, that potential energy curve goes like this. So, this is the width, this is the width of delta psi, from here to here is delta psi. So, you get a significant number of this delta psi by 2 pi is a significant quantity, like maybe 0.2, 0.3, and this could be significant, and efficiency can be achieved to be to the tune of something like 30%. To this you should also add the efficiency due to P2 effect that I mentioned earlier, plus the efficiency due to uniform or untapered Wigler, plus some more. But this is the prime term. So, by trapping a significant number of electrons in potential energy minima of the quantum motive force, you can extract much higher energy by tapering the Wigler. So, I think this is one thing that I wanted to discuss with you, that tapered free electron laser is a very fascinating concept, and it has improved the efficiency of radiation generation a great deal. Well, there are many variations of this device. The conventional or the major thrust of free electron laser research is employing magnetic wigglers. However, people can use different kind of ripples or waves as wigglers. For instance, people are thinking of having a X-ray free electron laser. Now the problem is that for X-ray generation you require the X-ray, the laser wavelength that you generate is equal to wiggler wavelength divided by 2 gamma 0 square. So if you want to produce a short wavelength, you should require either a very short wiggler period or very large beam energy. Gamma 0 is the Lorentz factor of the electron beam. So if you multiply mc square, it gives the energy. Now that is a very serious matter. You cannot have a conventional wiggler less than a few millimeter wiggler period. However, if you can choose a laser for this purpose, in that case it turns out that because laser has a frequency and wave number both, so from momentum conservation conditions you can find, and energy conservation, you get lambda of pump laser divided by 2 gamma 0, 4 gamma 0 square, and this could be a very short wavelength because gamma 0, lambda 0 could be like 1 micron. So this is one interesting thing. Secondly, as far as generation of millimeter waves, sub-millimeter waves is concerned, terahertz wave is concerned, one can use a gyrotron as a wiggler. Gyrotron can produce microwaves of very large amplitude and use them as a wiggler. One can also use a density ripple. Some people have examined the generation of terahertz radiation in a plasma with a density ripple. Density ripple can also act as a wiggler. The thing is that you need to compensate for the momentum and energy balance or energy and momentum loss by the particle, and that can be done in a variety of ways, though the most effective way to date is to employ a magnetic wiggler, but other schemes are also coming up. Now before I close, I would like to mention that one can view the generation of radiation by free electron laser as a parametric instability also. What you can do? You can treat the wiggler as a wave of frequency 0 and wave number kW. But to a moving electron, this will look like an electromagnetic wave travelling backwards. So suppose there is a wiggler like this and an electron is moving in this direction. To this electron, this wiggler will appear like an electromagnetic wave travelling in the backward direction, and Compton scattering, stimulator Compton scattering of that wave can produce radiation in the opposite direction. So to this electron, the wave is coming like this. This is the wiggler which appears like a wave, and electron beam is stationary, and Compton scattering of these wiggler wave photons in the backward direction will produce FEL. Well, analysis of this process is not difficult, and let me just give an outline of how to handle this problem. Suppose I consider my wiggler of frequency 0 and wave number kW as a quasi photon of 0 energy and finite momentum. It is exciting a beam space charge mode of wave number omega, frequency omega, wave number k, plus it produces a free electron laser photon or radiation of frequency say omega 1 and wave number k1. This is my radiation mode, this is my space charge beam mode. And for beam space charge mode is something like that. This is equal to typically k V beam plus minus omega p. This is the beam plasma frequency, this is the beam velocity, which actually is V0, I should call it V0. And this radiation mode has omega 1 equal to k1 c. The connection is that this k1 is the, or this k is the difference of this and this. So, basically you have k is equal to kw plus k1. So, what happens? The radiation wave and the pump wave, both these waves, this pump wave means Wiggler, they produce oscillatory velocities to electrons. They also exert a ponderomotive force at this frequency. So, the dynamics of the instability is like this, that Wiggler plus FEL radiation, they produce a ponderomotive force, and the ponderomotive force gives rise to density bunching, compression, rarefaction of electrons. So, this produces radiation bunching at frequency omega and wave number k plus kw. And this density bunching has a very strong, this produces a strong field, and this gives rise to a nonlinear current n omega k plus kw E into V, the electron velocity due to the Wiggler. So, and this produces a current at frequency omega and wave number k, omega sorry, this is omega is the same as omega 1. So, and this is k1, let me just write down this, this is k1 and omega 1 here, omega 1 k1 there, and this is minus kw actually, and sorry, this is k1 plus kw and k1 plus kw, not the complex conjugate, this is the same thing, and this produces a radiation, a nonlinear current at the frequency and wave number of the radiation, and that drives this. So, that is the interesting thing in here. This is a cyclic process, a feedback process in which the Wiggler and free electron laser radiation, they exert a force on the electrons. That force drives a density perturbation which is in resonance, phase resonance with the electron beam, and this is quite huge. Very small value of fundamental force can produce very large density perturbation, which goes as 1 upon omega minus k V beam whole square. So, this could be very huge, and this couples with the electron velocity due to the Wiggler to produce a nonlinear current at the frequency and wave number of the laser, and then they produce radiation. So, by this mechanism both the density fluctuation will grow as well as the amplitude of the FEL wave will grow. This process is known as Compton scattering. We have already learnt the two stream instability. In two stream instability also a beam drives a plasma wave via Cherenkov interaction, and this is the Cherenkov resonance that factor that appears in the denominator for the density perturbation, and that gives rise to very strong growth of radiation signal. Well, a lot of work on this process has gone. When the density of the electron beam is very large, then self consistent or space charge field of the this space charge mode should also be taken into consideration, and then the operation of free electron laser moves on to Raman regime. And I think there is a lot of literature available on that topic. Before the end, I would like to mention that a device very similar to Klystron has come up based on the concept of free electron laser. In a Klystron, what you have a buncher cavity, like this, and you have a catcher cavity. What happens? You launch an electron beam through here. If there is a small signal here, then that signal will modulate the beam velocity. So, when the beam emerges out here, so if there is a RF signal in this gap, that will accelerate some particles, and after half the wave period will retard some particles. So, you are getting a velocity modulation here. In a Klystron, this is a buncher cavity, this is a catcher cavity. So, when you launch an electron beam in such a cavity, and if there is a small noise signal here, then that will modulate the electron beam velocity. Now, the slow moving electrons that have left this cavity earlier, they will be caught by the fast moving electrons that come half wave period later, and they will bunch. So, that will create density bunches here that pass through the gap. So, density bunches are created like this, and they pass through this gap. They produce a huge electromagnetic wave at the frequency, same frequency at which the noise was here. So, if you can couple this waveguide to this, then part of the signal will go from here, and that will be more than the initial signal, and by this sort of feedback you can have a net transfer of DC energy of the electron beam into radiation energy into the catcher cavity and buncher as well. Now, this scheme has been utilized in the concept of optical Klystron. The concept is rather simple. This buncher cavity, the Klystron has a limitation that it can operate only up to a frequency like 10 gigahertz. If say I want to produce radiation in, suppose in the optical range, what should I do? I should reduce the buncher gap, but you cannot reduce it beyond a limit. So, what people found that replace this entire thing by some sort of a open resonator and bring a wiggler here. So, if I have a wiggler here, and this also catcher is replaced by another wiggler, this is there the mirrors for open resonator, this is a wiggler here. And launch an electron beam. Suppose I bring an electron beam here, and by using magnets you make it move inside and let it go out here. And then when it goes here, again make it bend here. What is happening here? You are having an electron beam coming from here. The beam enters the first cavity where there is a wiggler and there is a small radiation signal. So, that will both of them will exert a quantum force on the electron beam and will change its velocity or modulate its velocity. So, when the velocity modulated beam arrives in this space, this is called drift space, then this electrons which are fast moving, they will catch up the slow moving electrons which had left this cavity earlier. So, there is a charge bunching, and those bunches of charge, when they move through the second cavity, they will produce much enhanced radiation here, and you can get optical amplification. And this is a very fascinating device. So, here you have a split free electron laser into two segments, a buncher cavity and a catcher cavity, and I think it has a lot of promise. So, I think I would like to conclude by saying that Free electron laser has a lot of promise for terahertz generation, for infrared radiation generation, as well as for higher frequencies in the visible, in the ultraviolet, and even X-rays, X-ray generation. And the main requirement is the electron beam, because the energy is coming from the electron beam, and so a lot of efforts are being put into developing good quality, high current, high voltage electron beams at reasonable cost. The two areas are really directly coupled with each other. The accelerators, charge particle accelerators, and coherent radiation generation. Thank you.